Hi all, I welcome you all to the next lecture today. Today we are going to see the last segment of the eighth chapter, available and unavailable energy. Prior to this, in previous lecture we have covered the basic fundamental definitions of available and unavailable energy, and also we have seen the application of the availability concept to the non-flow processes as well as for flow processes. So we have seen two applications, right? One is on piston cylinder devices, another on rotary devices. And apart from that, we have seen the application of availability to the process and to the heat engine, and also we have seen one application on the heat transfer through finite temperature difference. What will happen to the availability of the system? Right. So today we will be starting our discussion from the point where we have left in the previous lecture. So today we'll see the useful work, maximum work. Right. Let me start my presentation here on. Uh, so if we want to know what is the availability, we have already defined the availability of a system is defined as the maximum useful work. Uh, if in the case of non-flow, we use to subtract the displacement work. If it is a flow processes, there will be no displacement work. That's why it is written, it has been written here. The availability of a given system is defined as the maximum useful work bracket total work minus PdB work that is obtainable in a process in which system comes to equilibrium with its surroundings. So the lowest possible temperature of heat rejection will be the surrounding temperature, as we are considering surroundings as our dead state. All right. So for a non-flow system, if we are going to write, then availability, that is maximum work, can be written in this way: E1 E minus E naught plus P naught B minus B naught minus T naught S minus S naught, where this is the work which has we have expended in displacing the boundary, right? So if we neglect the kinetic energy and potential energy term from the total energy will be the summation of internal energy plus kinetic energy plus potential energy. If we neglect kinetic energy and potential energy, we are left with only internal energy. So if you substitute that, right, you can write the maximum work or availability is given by U plus V naught V minus T naught S minus this term, and this term is also known as non-flow availability function, right? Either you can use small a or you can the phi symbol. So phi represent the non-flow availability function for the system, and this phi naught is for the surrounding. So this is the maximum useful work that is available. For a steady flow open system, as there is no displacement of boundary existing, there will be enthalpy and temperature need to be considered into consideration. So we can write the maximum work or reversible work as H1 minus T naught S1 plus kinetic energy plus potential energy. Same terminologies are also used here. If we are going to neglect these kinetic energy and potential energy had, then we'll have left with only H1 minus T naught S1. This is one function, and H2 minus T naught S2 is another function. So work will be maximum when the mass leaving the control volume in the equilibrium of the surroundings. That means that state, or you can say the final velocity by which your flow is leaving should be equal to 0. So if that is the case, you can write the maximum work as H minus T naught S mb square plus mg at the initial energy, minus this is the final energy when kinetic energy had is not available, and this is known as steady flow availability function denoted by psi. So psi is nothing but H minus T naught S plus kinetic energy plus potential energy. In some of the applications, the kinetic energy and potential energy terms will not be there, so you are left with only H minus T naught S. This will be termed as a steady flow availability function represented by the psi. So don't get confused between this. Phi is for non-flow availability function and psi for steady flow availability function. Next one is irreversibility. I said irreversibility is the loss of energy, right? And why loss of energy will take place? There due to various factors. It may be frictional losses, it may be pressure losses, it may be heat losses through the system boundaries. Even though we assume these boundaries of systems are fully insulated, but reality none of the boundary can be made fully insulated. Some of the losses will be involved, and losses due to some other internal irreversibilities of the system. So all those losses, if you account for, that will contribute to the irreversibilities, right, associated with a particular process. So irreversibility is nothing but it is the difference between the maximum work which has been generated ideally minus actual work. If you take the difference of these two, that will give the irreversibility. So for non-flow processes between the equilibrium states, when the system exchanges heat only with their environment, irreversibilities, so we can write I is equal to, this is maximum work, right? U1 minus U2 minus T naught S1 minus S2, this term represents the maximum work, and actual work will be whatever work you are getting from the piston cylinder device, right? That is called actual work. So that is from the first law we can say inter energy minus Q, right? So this term is here. So if you solve this and this term will cancel out, you will get only T naught S2 minus S1 minus Q. So this Q is also T naught into delta S if you substitute. So this is for system basically, and this Q which is going to the surrounding, so that will be contributing to the surroundings. So I can say the first term as T naught delta S of system plus T naught delta S of surroundings. So delta S system plus delta of surrounding will be the delta S of the universe. So irreversibility is nothing but T naught times of change in entropy of the universe. So whenever you are calculating, right, as per the second law, you know that the change in entropy of the universe will always be greater than equal to zero, right? So irreversibility will also be greater than equal to zero because that statement follows. Similarly, for static flow processes, right, we can write W max minus W per unit mass. So this is simply W max is T naught S2 minus S1, and W will give us Q. So we'll get almost same sort of formulae at the end, that is nothing but I into T naught delta S of universe. So this quantity, basically this quantity, if we just focus on T naught and delta S, what is basically it is doing? Irreversibility is nothing but that is not in our hands, that is going to the surroundings, or you can say unavailable energy, right? So this quantity itself represents the an increase in unavailable energy or energy of the surroundings. So T naught and delta S is also known as unavailable energy, that is nothing but irreversibilities. Next one is effectiveness, how effective your system is. So effectiveness is defined as the ratio of actual useful work to the maximum useful work. So the useful output of a system is given by the availability, basically whatever you are getting at the surroundings. So effectiveness is nothing but increase of availability of the surroundings divided by the loss of availability of the system. So for a compression or heating process, we can say it is an increase in availability of the system to the loss of availability to the surroundings. So this is nothing but unavailable energy, right? And this is available energy. So we can say useful work divided by the maximum useful work. So is the ratio of useful work, or you can say the work which is available for conversion, right, at the end, divided by the maximum useful work. This ratio will give the effectiveness, right, of a particular system. So effectiveness of an actual process always less than unity, because useful work will be lesser than the maximum work. So it will be always less than 1. Next topic is first and second law efficiency analysis. So first law efficiency nothing but simple what we have already defined: thermal efficiency of heat engine, then coefficient of refrigerator, coefficient of performance of heat pump. So first law efficiency is defined as the ratio of useful output energy to the necessary input energy. So if we are defining for the heat engine, it will be net work divided by the heat supplied. Alright. So the first law of efficiency nothing but useful or desirable output energy divided by the necessary input energy to be supplied. So if we consider the case of heat engine where source temperature is T1 and the sink temperature is T2, and it is producing some work getting in heat Q1. So simply we can say what is output is W and input is Q1. So this will give us the first law of efficiency. So first law of efficiency is nothing but W by Q1, or so simply Q1 minus Q2 by Q1, or 1 minus Q2 by Q1. So it is basically talking about the quantities. So Q2 will have its own magnitude and Q1 will have its own magnitude. It's basically a quantitative measurement of the effectiveness. All right. So if we look at the first law efficiency drawbacks, right? First drawback is it deals only with the quantities of energy, disregarding the type of or grade of energy. It doesn't talk about which grade of energy it is, right? So it is talking about just quantitative analysis of the efficiency. So it does not differentiate between energies available at different temperature. It doesn't talk about this much energy is available at this temperature, this much energy is available at this temperature. So these are basically two biggest drawbacks of the first law of efficiency. So these drawbacks basically make us to think about another way of representation of the efficiency, that is also known as second law efficiency. And this is general statement, right? Any process or cycle which is not while satisfying the either first law or second law of thermodynamics will not be possible, right? So this is nothing has to do with the second law of efficiency, but this is a general statement. So if we look at the second law of efficiency, so second law of efficiency is defined as the ratio of minimum exergy transfer associated with a process for a given system to the maximum possible exergy transfer associated with the same process in the same system. So exergy is nothing but available energy. Already I defined exergy is another name of available energy. All right. So we can say in other way, it is the minimum available energy, right? Associated with a process to the maximum possible available energy for the given process, right, at the same system. So we can say second law of efficiency in the minimum exergy or minimum available energy. A is representation of available energy minimum, Y available energy maximum. Alright. So for a closed system, if you are defining for a closed system, it will be defined in terms of A. This A is nothing but basically we can say this is per unit mass. This is total available energy, right? A minimum by A maximum. For open system, we will define in terms of B, because see, try to recall in closed system we have defined the non-flow availability function by is small a, and in the case of open system we have defined the Keenan function, that is by b. So that's why this terminology we are using here. So a minimum by a maximum, a b minimum by b maximum. So second law efficiency of heat engine, if you want to define, that is nothing but efficiency of actual heat engine divided by efficiency of reversible. This R represents the reversible heat engine, and this not is representing that reversible heat engine is operating between a temperature T and the temperature of the surrounding. So the lowest temperature will be the temperature of surrounding and maximum temperature will be the temperature of source. So second law of efficiency of heat engine will be defined as the actual heat engine efficiency divided by the reversible heat engine efficiency, which is operating between the given temperature source and atmospheric temperature, right? T naught. Similarly, next parameter is called relative efficiency. When you are defining the relative efficiency, it is the ratio of actual efficiency of heat engine, right, or you can say efficiency of actual heat engine divided by the efficiency of reversible heat engine. So this ratio is known as relative efficiency. But second law of efficiency talks about efficiency of actual heat engine to the efficiency of reversible heat engine, which is operating between a given temperature source and the temperature of the surroundings. So the lowest temperature will be surrounding, but in this case, relative efficiency, lowest temperature will be the actual temperature of the sink. So if we are defining for heat pump, so we take the consider the case of heat pump, right, which is basically taking the heat from low temperature reservoir and sending the temperature to the high temperature reservoir, and because of that it requires some work input. So, if you try to recall from the second law of thermodynamics, what is the reference that is called low temperature and body for the heat pump? For heat pump, low temperature body will be the atmosphere, and high temperature body will be the region where we want to maintain a temperature higher hot temperature, right? So this reference T2 is basically atmospheric temperature from where it is taking the heat and supplying to the warmer region. So second law efficiency of heat pump basically is nothing but coefficient of performance of heat pump. So it will be the ratio of coefficient of performance of actual heat pump to the coefficient performance of reversible heat pump operating between the temperature T and T naught. So when you are calculating this curve R H P naught, in that case you need to write this T2 as T naught, and this will be the source temperature, right? So efficiency of this heat pump operating between T1 and T2 divided by the coefficient of performance of heat pump operating between T and T naught. If you take the ratio of these two, will give the second law efficiency of heat pump. If we are defining for refrigerator will be something like this, right? Refrigerator is taking heat from the low temperature body and sending to the high temperature body. So in a refrigerator, basically, that's why we are saying evaporator is the region where we get the cooling effect, and condenser is the region where we are removing the heat to the surrounding. So in this case also we will define the second law of efficiency like a heat pump we have defined. Coefficient of performance of refrigerator, actual refrigerator operating between T1 and T2 divided by the coefficient of performance of reversible refrigerator operating between T and T naught. So here we can say this is the actual COP, that is Q2 by W, and The reversible cop of the refrigerator operating between T and T naught will be something like T2 divided by T naught minus T2. All right. So if we divide this, right, these two, right, we can say here now question will rise, why we are not representing this as T naught. This is not T naught basically. In the refrigerator case, the warmer area will be the atmospheric temperature. So T1 will be replaced by T naught. Don't make this mistake. So in refrigerator, right, the warmer body will be the atmospheric. So T1 will be replaced by the T naught in the case of refrigerator. But in the case of heat pump, the warmer body is my region, right, region where I want to make high temperature, and the lowest temperature will be the atmospheric temperature. So T2 will be replaced by the T naught in the case of the heat pump. But in the case of refrigerator, this T1 is replaced by the T naught. That's why it has been written here. So this ratio will give the second law efficiency of the refrigerator. Next one is gas turbine. So if we look at the gas turbine, the purpose of gas turbine is to generate the mechanical work output, right, from a momentum of high temperature gases which are going to expand. So the at entry temperature will be more, at exit temperature would be less, and due to this momentum transfer, right, we will be extracting the mechanical work. So the efficiency of gas turbine is nothing but shaft work which you are getting out of it divided by the input what you have basically given input, you have given the heat, right. So if you apply the static flow energy equation between point 1 and 2, you can find out the heat input, that is nothing but h1 minus h2 plus c1 square minus c2 square by 2 plus cz1 minus z2. So this is nothing but total energy which you have supplied, and what you have got, that is shaft work you got, ratio of this will give the efficiency of gas turbine. So the second law of efficiency of gas turbine will be what is you are getting out of it divided by the maximum possible. So maximum possible is only possible when all the processes are reversible in this case. So that is nothing but B1 minus B2, right. So these are nothing but Keenan function. We have to apply the steady flow availability function to find out the maximum availability of the gas turbine. So this is the actual work which you are getting divided by the maximum possible work of the gas turbine. If you divide these two, you will get the second law efficiency for the gas turbine. Similarly, for compressor, you can get, so in compressor case, right, actually it will be requiring more. Actually, when we are talking about actual performance, in that case, losses will be more, right. So those losses will also be added into the work. So, counter those losses, you have to spend more work. So the actual work requirement will be more compared to the maximum, the minimum work requirement. So here ratio is entirely different compared to the gas turbine. So here this is the minimum work which is required, V2 minus V1 divided by the actual work. This ratio is nothing but second law efficiency for the compressor, right. Or in per unit mass basis, you can say V2 minus V1 divided by small w, as this per unit mass basis, this is total basis, right, total mass basis. So if you look at the heat exchanger, the purpose of heat exchanger to exchange the heat from hot fluid to the colder fluid. So arrangement is something like this. Hot fluid is going from this pipeline, and there is a water jacket, right, through which water is flowing from this side direction and taking away the heat and coming out here. So Tc2 is greater than Tc1 and Th1 is greater than Th2. So which kind of heat transfer is taking place? A momentum is convection form of heat transfer is taking place. So the second law of efficiency of heat exchanger will be called as exergy gained by the cold fluid, or you can say the available energy gained by the cold fluid divided by the available energy lost by the hot fluid. So hot fluid will lose the energy, and cold fluid will gain the energy. So the energy gained by, or exergy gained by the cold fluid divided by the exergy lost by the hot fluid, this ratio will give the second law efficiency for the heat exchanger. So if you want to know how much energy has been gained, so you need to find out the availability of the available energy of the cold flow, that is given by the BC2 minus, this is an open system basically. Mass is entering, mass is going out, and energy transfer is also taking place. So we can say the mass of cold fluid, right, and available energy. So we can write BC2 minus BC1, and when you are writing the BC2 and BC1, you need to write H minus T naught S. These are the functions, right, Keenan functions, divided by the mass of hot water or hot flow, and BH1 minus BH2. Why BH1? BH1 means temperature at 1 is higher than the temperature at 2. So it has to be going like T1 minus T2. Here T2 is more than T1, so that's why we are writing BC2 minus BC1. So these are nothing but functions, right? So when you expand it, you will write H minus T naught S1 minus S2 minus T naught S2, and finally you will find out the entropy change and enthalpy, and you substitute here to get the second law efficiency of the heat exchanger. Similarly, mixing of two fluids, so if we take the case of mixing of two fluids, the two fluid streams are coming, they are getting mixed, and finally they are making one. So let's suppose this stream 1 is having high temperature compared to the 2, and both are going to mix to a final common temperature, and they are coming out here. So we can say M3 is equal to M1 plus M2, and T3 what you are getting is a mixture of it. So by applying the energy balance, you can find out the T3 as well. So second law of efficiency of mixing will nothing but the exergy gained by the cold fluid, right, divided by the exergy lost by the hot fluid, right, basically. So whatever this will lost, that will be gained by this. So we can say second law of efficiency of the mixing is nothing but this is cold fluid, right, this is the hot fluid. So we can say M2 how much it is gaining? It is gaining with respect to the T3, right? T3 and T2, this difference will be the gained, right, gained energy by the cold fluid, and lost energy T1 and T3 in between, we can find out the lost energy by the hot fluid. So we can say mass of 2 B3 minus B2 divided by mass of 1 B1 minus B3. Keep in mind, don't make any mistake here, T1 is greater than T3, that's why writing B1 minus B3. Here T2 will be lesser than the T3, so we are writing B3 minus B2. So once you put the value of these functions, right, these are Keenan functions, so you can find out the exergy gained by the cold fluid and exergy lost by the hot fluid. We take the difference, take the ratio of these two, we'll get the second law efficiency of the mixing process. All right. So that's all. So this with this derivation part of available energy and unavailable energy is over, right? So I will show you the summary part of it. All right. So summary, we have defined the available energy. So available energy nothing but W max, that is nothing but Q1 minus T naught divided by T1. So if you expand it, you can get Q minus Q T naught by T1, that is nothing but net Q2, right. So Q1 minus Q2 difference is called network. So if you expand this, right, you can write Q is equal to CPT, right. So MCP integration between T naught and T1 minus T naught by T into dt. So if you integrate this, you can write only T1 minus T naught into delta S. So W max is nothing but T1 minus T naught delta S. If you separate it, you can write T1 into delta S minus T naught into delta S. T naught into delta S will be the heat rejected, and T1 into delta S is basically heat supplied. Ratio of these means difference of these two will give the maximum possible available energy. So this another way you can write this as U1 minus U2 minus T naught S1 minus S2. This is for closed system. Clear? And for open system, the same this thing available energy can be written as H1 minus H2 minus T naught S1 minus S2, because in open system displacement work will not be available, and internal energy term we cannot define for open system. So in that case, it will be H1 minus H2 minus T naught S1 minus S2 for a steady flow system. Decrease in available energy for the finite temperature difference, if we look at this is the case, right, which we have proved there. We have clearly seen that heat rejected in the second case was higher than the one, so the work produced in the second case was lower than the one, so that much loss of work was happening due to the heat transfer through finite temperature difference. And when we find out that was equal to the increase in unavailable energy of the surrounding, that is given by T naught into delta S dash minus delta S. So you can say T naught into delta S of universe will give the decrease in available energy or increase in unavailable energy of the surrounding due to the finite temperature difference. Third case, the availability function we have find, right, H minus T naught S kinetic energy plus potential energy, right. So availability itself is nothing but maximum work output, maximal useful work. For a steady flow device, right, we can simply say in terms of enthalpy, right. So H1 minus H naught minus T naught S1 minus S naught, kinetic energy and potential energy. In most of the cases, kinetic energy and potential energy term can be neglected. If you are going to neglect these two terms, I can simply write H1 minus H naught minus T naught S1 minus S naught. Right, this is availability for the steady flow system. For a closed system, it is a non-flow availability function which is given by U minus T naught S, all right, plus P naught V. So if you take the difference of these two, right, that will give the availability for the closed system, which is given by U1 minus U 0 minus T 0 S1 minus S 0 plus this term which you are seeing here, P 0 V1 minus V 0. This is the amount of work which you are spending, right, to displace the boundary, right. This will come only in closed system. So this term, what is called, if you rearrange these terms, right, you will get this kind of form, right, phi 1 minus phi 0, you can write here, that is called non-flow availability function. If you look at the unavailable energy is basically defined as the loss in availability. So loss in availability is nothing but the heat which has been gone out. So that is nothing but T naught into delta S of universe, right? Or you can say T naught S1 minus S2. So this S2 is basically nothing but the entropy of the surroundings. So you can say T naught S1 minus S0 is unavailable energy. So increase in unavailable energy is nothing but loss in availability, right? Increase in unavailable energy, nothing but loss of availability. That is nothing but T naught into delta S of universe. So delta S of universe is always greater than 0. So increase in availability definitely is greater than 0. So with this, I think so we have covered the total, fundamental concepts of available energy. So I am stopping the today's discussion here, right? In next class, we will see some solved examples on availability function and available energy, unavailable energy, and second law efficiency. So if you are having any doubt in the concept which we have covered today, feel free to contact me either via WhatsApp or you can write in the comment section. Clear? So my advice is please revise the thing before coming to the next lecture where we will be discussing a number of numerical problems on availability, right. So total concept is we have seen the example, means application of availability to the non-flow processes, right. So where we have defined the non-flow availability function. We have also seen the application of availability to the open flow system or open systems, right, where we have defined the steady flow availability function. Apart from these two functions, we have defined the Keenan function, Helmholtz function, and a Gibbs function. Right, Gibbs function. Helmholtz function is applicable for closed system, and Gibbs function is applicable for the open system or flow processes. Flow processes. And then last topic was the first and second law efficiency, where we have defined the second law efficiency based on the grades of energy. We have clearly defined in terms of available energy at the system end and maximum possible available energy. So we have seen four different cases, right. We have defined second law efficiency for the heat engine, we have defined for heat pump and refrigerator, and apart from that second law efficiency for gas turbine, compressor, and heat exchanger, as well as mixing of two fluids. So we have seen how to find out the second law efficiency. So these are the main topics, right, for the available energy concept. So we have covered all the things. Please revise the thing, and when we are coming for the next lecture, right, where we will be doing numerical problems based on all these concepts. Everyone must have calculator with you. That is must requirement, right? Otherwise, by just looking at the solution, you cannot easily identify how actually things are going on, and until and unless you are not practicing it, it will be very difficult to keep the things in your mind. So that is very very must. So in next class I am expecting that everyone must have calculator with you, all right, and pen and paper. That is very very must. So even though it is a very silly thing which I am actually saying to you, now you are in second year of BTech program in mechanical. I think so you may be having habit of having not note and paper, pen and paper, as well the calculator with you, because engineers man weapon is calculator. If you don't have calculator, you cannot manage this numerical problem. That is actually expected. So regarding these topics, right, in the previous lecture and this lecture, if you are having any doubt, feel free to post in the comment section, or you can contact me on my WhatsApp number already I shared with you. All right. So see you all in the next class with a new topic. All right. Have a nice day. Good day.